Great, welcome back everyone. We are now going to be on page number 63 of our notes. And let me share my screen. And here we go. And let me go for my current slide. Again, we're on page number 63. All right. And of course, I need to figure out how to change my display. Okay. When we talked about the Bohr model, we talked about electrons gaining energy and being able to jump up to another energy level and then going back down to where they originally belong. So, and I mentioned the terms excited state and ground state. So we're going to get a little bit more detail than that. And then again, where this is page number 63 in your notes. All right, so what is the ground state? So when you think of ground, what do you think? Do you think of something that's higher or low? So when I think of ground, I think of low, right? So the electrons are at the lowest possible energy level. So then they fill in order from the first energy level up through the 7th energy level, filling in from lowest energy to higher energy. And in the lowest sublevel and orbital possible. So remember, your energy level is this like big area, like a hotel, right? And so here you've got your hotel, and now you have your sublevel, which is be like your floor in the hotel, and then the orbital, which would be like the room in a hotel. And so the orbital is the most probable location of the electron, right? So we're just really talking about electrons here, because chemistry is really mostly the study of matter and how matter interacts, and a lot of that has to do with what electrons are doing. So the electrons at the lowest energy level is called the ground state. So example, our carbon has 2-4. So that means that I have 2 electrons in the first energy level. So here's my nucleus. So let's do my 6 positive protons and my 6 neutral neutrons. And then I've got 2 electrons in the first energy level, and I have 4 electrons in the second energy level. Okay, so now that's their ground state. That means all the electrons are where they are supposed to be, and it is what is listed on the periodic table. So listed on your periodic table is the ground state. So now what is an excited state? Now an excited state is when we take electrons from their ground state, we give them energy, absorbs energy, and they're able to jump to a higher energy level. We call that higher energy level an excited state. Excited state. So let's look at our example for carbon. Now I'm going to say 1, 5. Wait a minute, what happened? I still have 6 electrons, right? So the same number of electrons, right? So I just want to make sure you just still have the same number of electrons. You're not adding or taking electrons away, because that makes ions. Those are charged particles. We're not talking about charged particles. We're talking about electrons jumping up to a higher level than where they're supposed to be. So then instead of 2 in the first level, I went from 1. And so where did that 1 go? It went up to the next level. So here I have my nucleus. And so I only have 1. And then now I have 5. So 1, 2, 3, 4, and 5. So one of these decided to jump up a level. But in order for an electron to go up a level, you can't just jump without expending some energy. You got to add some energy to jump to a higher energy level. Or I could also say 2, 3, 1, right? So I could just do 2 and then 3 and 1. So 3, 4, 5, still 6 electrons. So basically, you're just taking an electron, you're moving it up an energy level. You should be able to write an excited state electron configuration. You just have to show 1 electron moving up to another level, making sure you do not violate the 2n squared, right? So then you cannot violate our maximum number of electrons in any energy level. The first energy level can only hold 2, the second level 8, right? 2, 8, 18, 32, and so on. So now what is the electromagnetic spectrum? So it's all forms of light energy. So it's classified by wavelength and frequency, right? That's really, talks more about that goes into more of the physics realm. But here is what we call spectrum, right? Anything that is a spectrum is just a wide range of things. And so here is our visible light. So here's our rainbow. This is what we see, right? So the red, orange, yellow, green, blue, indigo, violet. But there's different wavelengths of light and different frequencies, right? And so we have UV, right? We have UVA, we have UVB, we have infrared, right? We have microwaves, radar, radio, TV, and we also have something that is called gamma rays, which is radiation, and our X-rays, right? So then these are like much, much higher energy wavelengths of light. Which leads us to the bright line or bright line spectrum if we're talking about singular. So you did learn a little bit about this in earth science, and this is how we identify which elements are present in stars. This is what you did in earth science. So anytime we heat, an element, it doesn't necessarily have to be a gas, but gases are definitely easier to heat up, causing electrons to travel to an excited state, right? So you add energy, electrons jump to an excited state. This is how light is produced. All light is produced by electrons, and electrons moving from the excited state back down to the ground state. So when they return to the ground state, right, what goes up must come down. So add energy to go to the excited state, release energy to go down to the ground state. And then when they go back down to the ground state, they release that energy in the form of colored light. And every element has a unique color or a unique bright line spectrum. Remember, everything in the universe is really some sort of high to low, phenomenon. So we go from high energy to low energy is how the light is produced. It's not when the electron goes up that the energy and the light is produced. It's when the electron goes back down that it's produced. So then from excited state down to the ground state, that's where the light gets produced. So each element has its own unique bright line spectrum similar to a fingerprint. No two individuals have the same fingerprint, not even identical twins. I teach forensics, so I should know. So your DNA, right, is also unique to you unless you're an identical twin, and then your DNA is unique. But there's no such thing as identical elements because there are no two elements that are identical. So every single element has a unique bright line spectrum because no two elements have the same electron configuration because no two elements have the same number of protons. And so when those electrons go from the excited state after they've absorbed some energy, they have to release that energy in the form of light. And then this is how our bright line spectrum is produced. And so we can look through a spectroscope and we can identify, and this is the basis of spectroscopy for forensics. This is the basis of identifying elements present in stars as well. So if I need to figure out what an unknown substance is on a victim or on a suspect, they're going to use spectroscopy. They're going to figure out the chemical composition, and they're going to use some form of this bright line spectrum. So no two elements have the same bright line spectrum. The bands will be different. And in order to figure out what a mystery element or a mystery substance is, you just have to match the bands, and every single line would have to be present. So if I look at sodium here, because it's the simplest one, if I have these three lines present at those specific locations in that bright line spectrum, then you can say sodium is present. But if I'm missing one of those yellow lines, then it wouldn't be sodium. And so we use what's called a flame test. And this is a lab in which metal solutions are heated in an open flame like a Bunsen burner, and the electrons are excited, right? How did they get excited, right? We heat them up with a Bunsen burner. When they return to the ground state, they give off the colored light. This is where colored flames come from. This is where fireworks come from. Different metals produce different flame colors, right? So we can produce different flame colors based on the different elements that are present. And so this is the basis of fireworks, sorry, not color work. So a red firework is because they have packed that firework with strontium, which produces a very bright red flame. If you have a green fireworks, there's usually, copper present in those fireworks because copper makes for a very nice green flame. The hardest firework color to produce, however, is blue. There's not really, you have to get the right combination of, different colors in order to produce the blue fireworks. All right, so how does a firework work? You have to light it off, right? So now you're adding energy. Then you've got this explosion, right? Because you've got some gunpowder or some other explosive type of material in there, which then adds further energy to those electrons. The electrons go up to an excited state, and then when they return to the ground state, what you're seeing is the light that's produced by the electrons going back to their ground state, back to their low energy level from the higher level, from high to low. All right, so we'll practice more identifying unknowns and the flame test, and we'll see you in the next set of notes will be mostly practice, and that wraps up our unit notes.